ci sono domande, ci muoviamo verso l'ultima presentazione. So the last talk is again by George van der Voort and is on metallographic studies for failure analysis.
So.
Please, George.
Okay. On my website, I have a number of different things about failure analysis. And a couple days ago at the University of Ferrara, I gave a talk on metallography and failure analysis, which was a shortened version of what's on the website. But I have a couple articles on conducting the failure analysis. I have a PowerPoint on that subject. I have a PowerPoint on fractography, also failures due to material problems or in manufacturing problems, and failures due to service problems. So if you're interested in this subject, you can find a lot more on the website. Also, I have failure studies on the 3 Mile Island Unit 2 nuclear reactor. How hot did the lower head get? How close was it to meltdown? And also failure of cables used to hold semi-submersible oil rigs steady in the Gulf of Mexico that broke during hurricanes. So there's a number of other things there too. In the Metals Handbook, I have a number of articles on failure analysis as well. Here, I'm going to just present information on, very detailed information on several more complex failures as an example. And I want to start off with the failure of a Loran C tower that was a type of Loran used for ships and planes to navigate. That was the towers were started around 1965 or so, and they were built over the next 10, 15 years before they switched to a different Loran approach than the C-type. This tower that failed was built on an island off the coast of Greenland, and the island was sacred Eskimo Indian burial site. Now, this involved a court case of the United States Coast Guard versus 3 companies, and I was working for Bethlehem Steel. These were the only 3 companies that were involved in the creation of these towers. So when the failure happened in around 1967, it had only been in service for 289 days. 1 guy wire broke and the entire tower collapsed, and it was 1,350 feet tall. And the Coast Guard hired a lab in Pittsburgh, Pennsylvania, to do a study on the failed, a pin that was in the tower broke. Loran tower is very low frequency signal. And of course, if you have a tower that's 1,350 feet tall, you have very long guy wires going from the top down to the ground, and those would absorb the signal that the antenna is trying to send out. So what they have to do is break up the guy wires periodically with insulators. So it's not one continuous long wire now. And the insulator was made of porcelain. And I think you probably heard about porcelain in the last presentation. It has very good compressive strength, but it does not have good tensile strength. So the cable is loaded in tension, right? When you're setting up guy wires. And so the insulator must be loaded in compression inside the tensile line. And to do that, they would put a pin of carbon steel, it was 1035 carbon steel, called an eye bolt. And there's a bigger head on it. The pin, of course, is hot dip galvanized for corrosion protection because it's sitting in the atmosphere. And there was a tool steel ring underneath the head rubbing against the porcelain to adjust the orientation of the pin in the porcelain. And this one guy wire that broke had a pin that was cocked. It was not properly aligned, so there was a bending moment in the connection there, and that's where the failure broke. And only one guy wire broke, the whole tower collapsed. When this happened, the designers recognized immediately what they had done wrong, and they changed the design so that the pins would properly, you could not be misaligned. You couldn't get a bending moment in a pin. And also, they made the design more redundant. The original design was based only on static loading, not dynamic loading. And of course, on a lower-end tower, the dynamic loading is much more critical than the static loading. And actually, several years after this happened, this failure, they built a lower-end tower on the island of Iwo Jima in the Pacific Ocean. And that tower had 2 guy wires break, but the tower did not collapse because the designers recognized the deficiency of their design and also the problem with the pins, the eye bolts, possibly misaligning, causing a bending moment, which is going to concentrate the stresses. So a lot was learned from this. The tower, as I mentioned, was only designed from static loading, and there is a problem with dynamic loading. If the guy wire is not properly tensioned and the wind comes at a certain speed and angle, the guy wires can vibrate sinusoidally. This is called Aeolian Vibrations, and this actually happened in the tower. A night watchman who was working there on the site, no high school math, physics, science, nothing, he observed these wires whipping, the one that broke, whipping like this, twice. And he wrote down in his notebook the time, the date and the time, and what he saw. But he, of course, didn't understand this, and apparently the results were not reported to anybody. But that was a key aspect of the failure study. So there was a study that was done by this man at Pittsburgh Testing Lab, and he claimed that the eye bolt was not oil quenched and tempered. Now this is 2.5-inch diameter, 1035 carbon steel. And he looked at the structure and said, there's no tempered martensite there. They must not have heat treated it. But you can't get tempered martensite in an oil quenched 1035 carbon steel no matter what you do when it's 2.5 inches in diameter. So one of the things I did was to prove that it was oil quenched. And of course, the Coast Guard, because there were only these 3 companies involved in making all these towers, they didn't want to irritate these people and cause problems, so they waited 12 years after the tower collapsed before they sued the 3 people. So it's an interesting failure. Now, as I mentioned, the eye bolt was 1035 carbon steel, 2.5-inch diameter. It was rough turned with the head about 1/2 inch thick. A tool steel slip ring was under the head. The eye bolt was austenitized at 1580 Fahrenheit, oil quenched, tempered at 950 Fahrenheit, then hot dip galvanized. And Pittsburgh Testing Lab claimed it was not oil quenched, but air cooled or normalized because there was no tempered martensite present. Now, a fatigue crack started under the head due to bending movement caused by misalignment of the slip ring. Now, I want to mention one thing. When I was working on this court case, and this is back in the 1970s, the control of the evidence in a court case was not as tight as it is now. The Pittsburgh Testing Lab cut a couple samples out of the head one at the origin and one at the final rupture zone. And the sample at the origin disappeared. It was never available for us to look at. Today, that court case would have been thrown out because they did not preserve the evidence, and the people being sued did not have the evidence to examine to try and prove the case. But in those days, things were more loosey-goosey, and we had to do, they'd say, tough, do the best you can. So that was one aspect. The other aspect was I would work on some of these cases with a fellow at Homer Research Lab named Harold Riemsnyder, who was a world-class fatigue and fracture expert. And Harold was doing modeling of the tower according to its dimensions and the environment. And first he considered static loading only because that's how it was designed. And this is before we had pocket calculators, computers. This is like 1979, 1980 we were doing this work. And he had to do everything on a pocket calculator by hand. And modeling wasn't as well developed in those days as it is now. But when he calculated the life of the Loran tower based upon static loading only, he estimated it should last 600 years. Well, it would have corroded away before that. And then, of course, the technology would be long obsolete. Then he added in the bending moment in the pin, the eye bolt. And his calculations estimated it should have lasted 30 years, right? Now, he took the data that the watchman had as to when he saw the Aeolian vibrations, and he went through the entire weather data for the 289 days the tower was up. And he looked at the same orientation for the wind and the same speed. And he estimated the total amount of time that the tower could have had these dynamic loading from the Aeolian vibrations. And his estimate of service life was 300 days, which is damn close to 289, Now, while he was doing this, he and I, we would work separately until we were both done, and then we'd discuss our results together, so that neither of us would be possibly influencing the judgment of the other. So while he was doing that, I was replicating the fatigue fracture and then determining how many cycles I could measure between close to when the crack started, because the man had cut the origin out. So I couldn't get to the exact origin, but as close as I could get to the origin to final rupture. Now that doesn't tell you how many cycles there are before the crack started, but nevertheless it would be more conservative because I can't estimate how many cycles it took before the crack started than what Harold would come up with. And so when I gave him my results, they fit in perfectly with his model, which is the way things should work when you do good work, but it doesn't always work that way. So first I looked at the proof of the heat treatment. Hardenability analysis showed that martensite cannot form in a 2.5-inch diameter oil quench bar of 1035 carbon steel. A 2.5-inch diameter bar of 1025 carbon steel was heat treated using oil quenching and air cooling with thermocouples to determine the cooling rates and microstructures. And then I had geometry bars of 1035 and 1026 that were examined to determine the microstructure as a function of cooling rate. So here is data for 1035 using geometry hardenability analysis technique that's oil quenched. And you can see the hardness profile going across the bar diameter is in the Rockwell B range, no martensite whatsoever. And the square box data points, that's the actual hardness measured on the pin itself. So you can see that the hardenability analysis versus the actual data was pretty consistent, except at the center, the actual hardness was even lower than what the hardenability analysis predicted. But certainly no martensite. You're never going to get tempered martensite at that kind of Rockwell B level unless you're annealing it, subcritical annealing it. Now, here's another example. This is 1035, 2.5 inch diameter bar. And you can see you've got the bar diameter across here on the bottom, surface, mid-radius, and center. The hardness in rock will be on each side of on the y-axis. Now, the theoretical hardness based on the geometry curve and hardenability calculations for an oil quench are the circular data points at the top. And then the actual hardness are the squares measured on the eye bolt. And the triangles down here are the predicted hardnesses if we had air-cooled it based upon the geometry data, right? And you can see the air-cooled hardnesses are down around 82 Rockwell B. The actual hardnesses are much closer to the theoretical for oil quenching. So we were trying to not only determine, you know, that it was oil quenched, but also that it was not air-cooled. Now, here are examples of the data that I got by using 1025 carbon steel, which is the closest thing I could find in the building, in the research center, that was the right diameter. And we put thermocouples in subsurface and center locations. And we're quenching this from 1580 Fahrenheit as the eye bolt was supposed to be austenitized at. And you can see the cooling rates here for the oil quench are much faster than the cooling rates for air cooling. So that data is very useful. Now here, we're going to a heat treatment simulation. I'm taking 2.5 inch diameter, 1025 oil quench from 1580. There's the composition of the steel. And you can see the subsurface cooling rate and the center value here. And we've got cooling rates of essentially 690 Fahrenheit per minute at subsurface and about 561 Fahrenheit per minute at the center. Now here is the air-cooled results. And you can see the subsurface is only 38 Fahrenheit per minute, 1/10, less than 1/10 of the cooling rate. And the center was 39 Fahrenheit per minute, much lower cooling rates. And here is the data for the 1025 2.5 inch diameter bar. Now, again, I used the geometry data, the whole calculation procedure to predict what the cross-sectional hardness would be, and also, you know, based on the tempering practice. And you can see the predicted oil quench hardness should be from about 85, maybe 85 Rockwell B near the surface to about 84 in the center. And the actual hardness that we got on the bars were slightly lower than that. And the center, again, substantially lower than the predicted value when it was oil quenched. But when it's air-cooled, we're down around 73 Rockwell B, substantially lower, indicating that this technique works. This is actual data. Now here is a geometry bar for 1035. Over the years, I've often used geometry bars as quenched, and then sometimes I'll temper them at the recommended tempering temperature and re-hardness test the bar to see what the hardness is in a tempered condition as a function of cooling rate. And I always would first, as quenched, I'd polish the geometry bar from about the end quenched end to a depth of at least 2 inches, maybe 2.5. But after that, you know, the geometry bar is 4 inches long. After that end part that's up near the fixture, the cooling rate doesn't change much in that area. So the critical part is at least from the end quenched face to a depth of 2 inches, or possibly 2.5. And there's well-known cooling rates that have been measured on geometry bars using thermocouples. And that data is plotted across the top. And you can find this kind of information in the ASTM standard A255, which is on the geometry hardenability test. So you can see here the as-quenched values. And notice, even very close to the water-quenched end, we're only a little over 101 Rockwell B. We're not anywhere near the Rockwell C range. And so, certainly not, if you had 100% martensite in a 0.37 carbon steel, you should be up around 45, 50 Rockwell C if you got 100% martensite. And after tempering, you can see the hardness is going to be lower, going to be substantially lower, which is exactly the kind of numbers that we see in the actual pin. And here's the same data for the 1026 carbon steel geometry bar as comparison. Of course, it's lower carbon, you can have somewhat lower hardness. And here we're plotting the hardness versus cooling rate for the 1025 and the 1035 steel on the same curve. And you can see surface and center values and so forth there. And the air-cooled values are, see where these, it's in the lower, just below the center, slightly to the right, it says AC for air-cooled. You can see C and D are the kind of hardnesses that we actually got on the samples that are air-cooled, so you can pick off the cooling rates. Whereas up at the top, where you have the EB and the green arrows, that relates to the oil quench data, and also A and B are oil quench data. So big difference in hardness. Here's examples of the microstructures. On the top is oil quenched, on the bottom is the air-cooled or normalized condition. And you can see the left picture in both cases is the surface microstructure, the center is the mid-radius, and the right-hand side is the center. And these are all at 500x etched with nitol. And you can see we have nothing but ferrite and pearlite. In the upper left at the surface, we've got a little bit of bainite in there. But otherwise, at the normalized, it's all ferrite and pearlite. There is some bainite in the mid-radius location for the oil quenched, but not much in the center. And here's the actual microstructure of the eye bolt. Now, we're looking at two different magnifications. The top is 100x and the bottom is 500x. And you can see the difference between the surface, mid-radius, and center, that the surface has more pearlite, and as you go towards the center, you have somewhat less, and the pearlite is coarser in interlamellar spacing. So, you know, there's no tempered martensite in there, and of course there should not be if it's oil quenched. And here's the microstructure as a function of cooling rate for 1035 as quenched, not tempered. And we're going from 7,500 Fahrenheit per minute, which of course is far faster than oil quenching can do. And still, there's a little bit of martensite in there, but not a lot. But there is some martensite at that rate. But when we're down at the extreme right, that's about 600 Fahrenheit per minute, that's very close to the oil quench rate. And that's only ferrite and pearlite. Even at 978 Fahrenheit per minute, that's strictly ferrite and pearlite. And of course, as we get down near the bottom here, around 210 Fahrenheit per minute, that's like the air cooling rate. Now, I measured the percentage of ferrite as a function of cooling rate, and that's on the y-axis here. And the cooling rate in Fahrenheit per minute is on the x-axis. And you can see the oil quench results versus the air cooled. And the oil quench, you're down around maybe 25% ferrite. But in the air-cooled, you're up around over 50% ferrite, and the balance being pearlite. So we're using a lot of different approaches to try and prove that the damn thing was really oil-quenched and not air-cooled, as there was claimed. Another thing I did was look at the interlamellar spacing of the pearlite. And here is examples of carbon replicas of the pearlite viewed in the TEM, because we need high enough magnification to resolve all the lamellae, and then we're going to do spacing measurements of the lamellae. And you can see as we go to slower and slower cooling rates that the lamellar spacing is increasing, which is exactly what you'd expect. And here's results in the eye bolt, surface, mid-radius, and center. And those are fairly coarse spacings at the same magnification as the previous. So when we look at the cooling rate, and on the y-axis, this is the On the left is the log of the mean random interlamellar spacing. If you measure a directed spacing, you can't do much with that. What you want to do is a random orientation, use like a circular test grid, and get a mean random spacing, because that's exactly twice the mean true spacing. And that's been proven theoretically in the literature. And in one study, I did an exhaustive study to prove that from an experimental standpoint that this actually was true, and it is. And you can see the interlamellar spacing for the air-cooled versus the oil-quenched, and you see the eye bolt, the EB values, are virtually identical to the oil-quenched bar that we made in our experiment. So again, that's another way of proving that it was oil-quenched, not air-cooled. So in conclusions, hardenability calculations show that martensite cannot form an oil-quenched 2.5-inch diameter 1035 carbon steel. Hardness predictions for oil-quenched 1035 agree with data from the eye bolt. The percentage of ferrite agrees with the amount predicted for oil-quenched 1035. The interlamellar spacing of the pearlite for oil-quenched 1035 carbon steel agrees with the eye bolt measurements. And similar tests on 1025 and 1026 carbon steels demonstrated the validity of these calculations. We want to do extra tests to prove that this method works. Now, the fatigue fracture of the eye bolt was looked at, and static stresses cannot account for enough cycles to cause the failure. No way. That's why Harold's analysis, even with the bending moment considered, was claiming 30 years life, and it only lasted less than a year. So how many stress cycles were there of sufficient level to grow the crack? And can replication give us an estimate of the number of stage 2 cycles? And of course, when I got this job, the failure occurred 12 years before we were given the samples. So you wonder, what kind of quality is that fracture in? And the man had cut a piece out at the origin, and also the final rupture zone. Fortunately for us, he coated the fracture with grease. So when I got it, I could clean the grease off, and I could replicate it and see fatigue striations. Now, if any of you have done this kind of work, you know that in body-centered cubic metals, such as iron, fatigue striations are irregular in appearance. They're not uniform, and they're difficult to measure. Face-centered cubic metals, which are much more ductile than body-centered cubic, because they have close-packed planes, close-packed directions, whereas in a body-centered cubic, you only have one close-packed direction, no close-packed planes. So in face-centered cubic metals, you have better-looking striations to make the measurement. So this is a tough analysis. Now, here is a schematic that I created when I got the actual fracture piece. The head broke off. That outer band around is the larger head and the marks in the galvanized coating. The actual rim, the actual pin diameter is that solid circular part inside that. And you can see up at the top is where the man cut the sample out, where he did some metallography looking at the origin. And so I don't have the actual origin. And at the bottom, we got the final rupture zone. And those lines on the fracture at the top are the clamshell or beach marks for the fatigue crack growth. And the rough area on the lower right, that's the final rupture zone. So you can see that the beach mark, the fatigue portion, is much larger than the final rupture zone, which indicates the loads, applied loads, are relatively low. The bigger the portion that's by fatigue and the smaller the portion by final rupture, that means the applied loads are low. If we have a very small fatigue crack portion and a very large fracture, overload fracture zone, that means the stresses are quite high. And of course, we can't see the origin of the failure, but it appears there was only one origin location, although it's been cut out. which would indicate that stress concentrators are not a serious problem here. So these are examples of the striations that I could see in the different locations. Now, you have to be very careful because you can have fracture through the pearlite colonies, and you're going to see parallel lines that are very nice and uniform. That is the interlamellar spacing of the pearlite and has nothing to do with the fatigue crack growth. So you got to be careful that you don't actually measure the interlamellar spacing while you're trying to measure the striation spacing, and that can happen. So here's some data that I got from these different pictures that were just shown a minute ago. The replicated areas. Let me just go back here for a second. See the numbers from 1 to 11. This is the replicating tape, and I cut each of those pieces apart and put them in and ran through the normal process for making replicas in the TEM. And I started the analysis at the center of each of those squares because I knew the distance from as close to the origin as I could get on those squares. So eventually I've got to plot that. But these are the 11 locations. And those 6 pictures right here are different locations. So we're looking at the third column as the distance from what I call the 0 point, or as close to the origin as we can get in microns. And then I've measured the average, the mean random spacing, I've measured the striation spacing, a mean value based upon a number of measurements on each replica, starting near the center and working a little bit outward. And then in the right-hand column is the magnification that was used. And I'm plotting that now. On the x-axis, we're plotting the average number of striations per micron. And on the y-axis, we're plotting the distance from as close as I could get to the origin as possible. And then we're going up to at about 38,000, because that's 10 to the 3 microns, is where the final rupture zone was. So you can see the data points are my average striation measurement, and I then did a least square fit mathematically and drew that line. And then I graphically integrated under the line and made an estimate that from near the origin to final rupture, there were about 250,000 cycles strong enough to drive the fatigue crack and increase its length. But I can't say much about, or anything about, the cycles before the crack started, because there's no way to measure that. So, and I also did an experiment where I took a 1025 carbon steel sample and a Sharpie VNUT sample. I loaded it in an MTS machine and cycled it a certain number of cycles until I could see a visible crack. Then I stopped the cycling, I measured the depth of that crack. Then I continued to cycle it for another 10,000, 11,000 cycles roughly, and then broke the sample. And then I did fatigue striation measurements, and I got a very close estimate from where the crack started to final rupture based from the fatigue cycles versus the actual number of cycles on the MTS machine to prove that this technique works. Now, so graphical integration showed approximately 250,000 cycles between the location near the origin and final rupture. Static stresses, of course, cannot account for that magnitude of stresses in 289 days. The watchman twice reported seeing a guy wire that ultimately failed whip in a sinusoidal manner, but he had no idea what he was seeing. But at least he recorded it. The analysis of the weather conditions at these 2 times and assessment of other times when the wind was at the same angle and speed agreed with the magnitude of stress cycles defined by fractographs. And the result was when we wrote our report, they dropped the case because they recognized that, you know, they had no basis. Now I want to talk about another failure. There's a company in the United States that operates trains between Lorton, Virginia, which is near Washington, D.C., and Stanford, Florida, which is fairly close to Disney World. And these trains, the train company is called Auto Train because you can load your car on the train and get a sleeping berth for you and your wife. And the next day you wake up in Florida and drive your car off for vacation or retirement in the wintertime. We call these people snowbirds. They're northerners trying to avoid the snow in the winter by going to Florida for a month or two or whatever. And so this failure occurred in February 1978. And at that time, Auto Train was in bad financial shape. They were actually in what's known as receivership, which is a part of the bankruptcy process. And technically, I don't know exactly the details about that, but they were in trouble. So Auto Train Unit 4, this was a drive locomotive, was entering Florence, South Carolina, and it derailed because of the fracture of the second axle on locomotive 4002. That was the number on the locomotive. They had a couple drive locomotives on this thing. What happened was it had a friction bearing made of bronze, lined with Babbitt metal, and the axle is about 9-10 inches in diameter and inside the friction bearing. And the traction motor to put the power to the wheels was partly supported on the friction bearing, and the rest of the support was on the main body of the locomotive itself. And the axle broke, and because of the friction bearing losing its lubrication, and then fell down. And as they came into it broke actually about 18 miles before it got to Florence, South Carolina. And when it got to Florence, there was I don't know if you're familiar with railroads, but on the track, if you're on this track, you're going straight on it no matter what. But if you want to switch to a different track, they have an X member in the track line that they can shift to move you to another set of rails going to the left or one to the right. And this X member is called a frog, and it has nothing to do with French people, by the way. But it's made of Hadfield manganese steel, which is the only steel with enough toughness and strength and wear resistance to hold up in this application. Because even though that train may only be going 2 miles an hour, you're talking about a huge amount of momentum because the train weighs, let's say, 40,000 tons, you know? And so what happened, of course, was as it's going into Florence, it wasn't changing the train, but the axle's hanging down, and it hits the frog, flips the train off the track, upside down. It was about 2:30 in the morning. 3 people were taken to the hospital, and they were all released within about an hour. Now, Auto Train was in deep financial trouble, and all the people running Auto Train, even though it was a relatively new train, had all worked at other railroads before. And they looked at this, and they knew damn well it was an overheated friction bearing. But the company was in trouble, so they decided to hire a company in Atlanta, Georgia, called Law Engineering. And this is NTSB, National Transportation Safety Board. They decided to hire this company to do a failure analysis. And the person who did the analysis work for Law Engineering was, he made no effort to learn anything about the failure mechanism. He had no understanding of liquid metal embrittlement, which is what's causing the failure. And his report talked about diffusion of copper from the friction bearing into the axle. And liquid metal embrittlement has nothing to do with diffusion. It's like drinking something with a straw, sucking the liquid up the straw. That's the grain boundary. So it's not diffusion, atom by atom movement. But Bethlehem Steel had made the axle according to the American Association of Railroads specification M101 grade F, which is a double normalized in temper. And it's 1072 carbon steel. And of course, you never get any martensite in an axle like that. So Letco, a law engineering test company, did not observe any, as they said, diffused copper, or the bearing elements, which is mainly copper, in the axle. And they claimed that the axle failed due to surface defects left in the axle by Bethlehem Steel. Now, finding surface defects or voids at the surface of an axle like this is virtually impossible, because that steel started out as a 30-inch diameter ingot that was hot rolled down to 13-inch round billet, and then they GFM forged. GFM is a forge from Austria. It has 4 heads and is high-speed hammer forging, and it forges the axle from 13-inch round down to the actual contour of the axle, which is somewhere around 8 inches in diameter. I've forgotten the exact dimension. But there's no way you're going to have defects at the surface. The only possible defects, voids, would be in the center line if that steel came from near the top of the ingot, which it did not, of course. So NTSB made inspection recommendations to the AAR Technical Committee, and the AAR Technical Committee did not agree with any of the conclusions from this man's study, because these people knew a lot about railroad products. On a previous trip from Lorton, Virginia, when the thing failed, it was going from Lorton, Virginia, or excuse me, Stanford, Florida, up north to Lorton, Virginia. But before that, the trip before, it was going from Lorton to Stanford. Now, the practice is, if you're running locomotives, is when you get out at the destination, a man usually comes out of the caboose at the end of the train, assuming there is a caboose, and he walks along, and it could be a woman too, of course, walks along and touches the ends of the journal of the axles. And if it's hot, he reports it, and then they go underneath the train and inspect to see if the lubrication is empty. The container that's holding the oil that is fed by a wicking mechanism into an opening in this friction bearing. The friction bearing is a cylinder about 1 meter long, made of bronze, and it's got an opening for the oil to come in, and the inside of the friction bearing is lined with babbitt metal. So, as I mentioned on the previous trip, they got a worm reading, but they failed to check on it, and of course the next trip, they only got as far as Florence, South Carolina, and it broke. And after the failure, they walked back and looked at the wooden ties from the failure state backwards and found marks from where the axle broken ends were hitting the wooden ties, and found that those marks stopped 18 miles south of Florence, which is where the axle broke. So the axle was obtained from Letco in December 1980, but they hadn't preserved the steel. They took 2 samples to, not Georgia Tech, but the University of Atlanta, and asked them to look at the samples in the scanning electron microscope and see if they could detect copper. But the man's polishing procedure was terrible, and they didn't detect any. But those 2 samples they took to the university, they lost. And all the pieces were heavily coated with rust. I went down to get the material. We hired a huge moving van who was big enough to handle a museum almost. I mean, it was much bigger than anybody would need for their house, just to take the remains of this axle back to Bethlehem. And it was a tiny area used on the train, on the moving van. But when I got there, they had the pallet with the broken axle halves sitting under a metal storage cover. But when I looked at it, everything was covered with a thick layer of rust. And I looked in at the axle sticking up, the other side that didn't break, has a hole drilled in it, and it's full of water. So obviously they had it sitting outside the whole time, and before we went there, they put it under the cover to make it look like they were protecting the evidence. But they were heavily rusted. And I had to get the court to allow us to remove the rust on some of the pieces that we could study. But before we did this work, because we had, in the research lab, we had never looked at a failure like this. So I called Seaboard Coastline, which is in Florida, and asked them, do you have examples of these kind of failed axles? And they said, the guy said, yeah, we got them by hundreds. And I also studied the literature back to in the 1800s, actually, because railroad's been around for a long time. And there's lots of articles published. There was a big article in Stahl und Eisen in 1914 of an axle made by Krupp that was sold to the SNCF in France that failed. And the French were suing Krupp when World War I broke out. And according to the article, they claimed that the French had put the axle in a lathe and turned the surface to remove the evidence of the overheated friction bearing. Anyway, so we got 2 axles. I asked them, can you give me one that had a lot of damage to the fracture surface, like the one in the actual court case, and also one where as soon as it broke, it stopped? They said, yeah, sure. So they sent us axle 1611, which had no real damage to the fracture, and 2028 that had a lot. And those are pictures of them. And here's a close-up of 1611. The commutator side and the drive wheel side. And this is the 2028. And this is really the way the axle looked on the auto train. So here's what I got back from the auto train. This is some of the samples. Look how they're covered with rust. And there's missing samples in here. It was unbelievable. He cut it up into 49 pieces. And you can see where the missing pieces are. They're the ones that he took to the university to look at in the SEM. And the other pieces had different codes and so forth. And I had to get the court to allow me to prepare some of them. You can see here about in the mid-height there, where the cutting ends, there's a missing piece there. And the lower half of the fracture, see where the number 1 is? You can see that 2 sticks out further, and the whole fracture surface on the lower half, they lost. Good preservation of evidence, right? So here you can see sample missing and the lower half of the fracture missing. And we got to do a failure analysis on it. Today, that case would be thrown out of court. Now, I got the court's permission to clean off the rust on some of these. And here's axle specimen 10 or CW3 coating. And you can see copper on the surface. Now, this was glass bead blasted, not shot blasted, but glass bead just to remove the rust. And you can see the cracks in there. The 2 axles we first got from Seaboard, I took down to the Bethlehem plant and we did X-ray analysis looking for the cracks with a powerful X-ray unit for crack detection that they have in the foundries there, or had in the foundries there. They don't exist anymore. And you could see cracks coming in the surface all over the region below the fracture, anywhere it was underneath the friction bearing, which was like 1 meter long. The failure always starts in the center because the temperatures are highest, the stresses are highest in the center. But the fracture is banging, and so the fracture is destroyed, and your first thought is, what can I prove without the origin? Well, in this case, it was no problem because there were secondary cracks all over the place, loaded with copper. So here's an example of SEM elemental maps and EDS spectrum on sample 17C. You can see the top picture is a secondary electron image. The second one is a backscatter electron image, which is showing more the atomic contrast difference between copper and iron. And then the bottom is a copper X-ray map. And over on the right, you can see 2 big copper peaks on the right, a small iron peak, a small tin peak, because it's a bronze, it's not pure copper. And then here's some additional mapping at higher magnification in the electron microprobe, which is better for mapping in those days especially than the EDSs and an SEM in those days. And you can see, look at all the copper in the lower left. I mean, and the iron is not in that zone. A little bit there's in there, but not much. There's tin in there, little antimony, a little bit of zinc. There's lead in there. And of course there's some oxygen, but not a lot. And here's a montage of copper penetration in sample 17C. All this yellow stuff at the top center is copper, and there's some in the lower pictures. And then at the extreme bottom, you see ferrite in the grain boundaries. And here's another example of montage setup. These are the days of using pictures and gluing them together. We don't have to do that now with the technology we have today with cameras. And I did some experiments looking at the growth rate. I made bars 11 inches long, and 0.505 inch diameter is a standard tensile bar diameter in the US. And in the center, I machined a V-notch to a depth There's a diameter at the depth, and the center of the V-notch was 0.375 inch. And I tested one bar first with no copper on it at 1100 centigrade, which is the temperature that you could probably get to in these failures. And it's well below the melting point of the steel, but it's above the melting point of copper. So that took like 589 pounds to break at 1100 C. And then we tested at various amounts of load, less than 589. And I measured the crack growth rate on these samples. And you can see the plot here is a beautiful correlation when we look at a log-log plot. So when we published these results, again, the case was thrown out by the court. Now, the last one I want to show you, which is shorter, is failed ASTM A490 high-strength steel bolts. These were put into the Collins Power Station in Morris, Illinois, which is not a nuclear power plant, but fossil fuel. They had 1 1/8 inch diameter bars, bolts, that were 8 and 11 inches long that failed soon after installation. These bolts were going through structural steel members, and they would tighten the nut on the bolt by hand and then take a torque wrench and give it another turn. It's called the turn of the nut method. And the standard practice is the next day, someone comes in with a hammer and taps the heads of the bolts, and these fell off. This is very bad, obviously, right? So they had failures of 11-inch long bolts that initiated by minor surface forging defects in the head shank fillet area. And one 8-inch long bolt started out a semicircular shaped crack that appeared to be a quench crack or possible stress corrosion crack. So ASTM A490 is 4140 alloy steel. The bolts were used in a girder splice. The temperature of installation was 20 to 40 Fahrenheit when they did the turn of the nut method. And 2 bolts failed immediately after installation when the installer tapped the nut part with a hammer, and the heads fell off. This was a standard head integrity test. And others were actually found broken the next morning without any banging of the heads with a hammer. The bolts contain 0.023 to 0.025% phosphorus. It's a bit on the high side. It's legal according to the spec, which is 0.045 max, but it's high. And the hardness of the bolts were 4243 Rockwell C, which is a little on the high side, but especially A490, you're supposed to be in the 30 to 36 hardness Rockwell C range. The tensile strengths were 192.9 to 196.3 KSI, which is well above the upper limit of 170 KSI. So they weren't tempered at the right tempering temperature. The elongations were 12 to 13%, but the minimum required by the spec is 14. So the 50% ductile fracture appearance transition temperature of the broken bolt at 42 to 43 Rockwell C was plus 85 F, and the 15 foot-pound impact strength transition temperature was plus 55 F. That's not very good. For a bolt retempered to 35 Rockwell C, which is within the range, the spec at that time was 32 to 36. I think it's 30 to 36 now. The 50% ductile fracture appearance transition temperature was minus 55 instead of plus 85. That's a huge difference in the impact transition temperature. And the 15 foot-pound impact strength transition temperature was minus 140 instead of plus 55. So you can see a huge difference in toughness. Retempering at 1100 F, which removed the phosphorus segregation to the pyroxene grain boundaries, made a remarkable improvement in toughness. Here's examples of some of these failed bolts. And you can see they're failing in the thread. It's usually the first thread that's engaged in the nut. Here's the bolt 1 and 2 where you had these strange origin zones. And in bolt 1, you can see at the origin at 1000X, it's intergranular. And even the center bolt fractures predominantly intergranular. And there's some secondary intergranular cracking going off the main fracture. And here's bolt number 3. This is a gouge at this bolt surface that initiated the fatigue. But, and so that's the initiation site. But in the center of the bolt, again, it's intergranular. And here's some other examples. Bolts 1 and 2, you can see those circular zones near the bottom where the arrows are. Those are these strange initiation sites. But you know, at that hardness, this bolt would be sensitive to chloride ion stress corrosion cracking if there's any chlorine in the environment. And I don't know whether there was, but you can see they're intergranular. And the other bolts have different kind of patterns. And there's geometry, Rockwell geometry data in Rockwell C, as quenched, and then 900, 1,000, and 1,100 Fahrenheit. Because I tempered, I made geometry bars, ran them, and then I also tempered them and ran the hardness. And this is percent martensite versus geometry bar location. And you can see that at a distance of 0.35 from this, on that first one there, we've got about 85% martensite. And it keeps dropping down because we're in the inflection zone. If you're up in the high, near the beginning, the water quenched end, it's all martensite. And these are data based on measurements made on a geometry bar from the steel, percent martensite versus as quenched hardness. And you can see when we're 100% martensite, we're up around 60 Rockwell C. And as we drop in martensite, we're going down. But and this is tempering practice established to meet the hardness range. 32 to 36 is the hardness range. And the solid line is high carbon, high alloy content, because there's a composition range to 4140. You know, there's a certain range of carbon, chrome, manganese, and everything. And so I calculated the hardness as a function of bar diameter and tempering temperature based upon the top of the limit and the bottom of the limit, and for getting 32 or 36 Rockwell C. So we could have really good data to decide what tempering temperature to use. So in conclusion, the failed bolts contained 0.023 to 0.025 phosphorus, were well above the specification range in hardness. At 32 to 36 was the spec at that time. They were above the tensile strength limit and below the percent elongation limit. The failed bolts exhibited intergranular fractures due to being temper and brittled, as the tempering temperature, which I estimated was somewhere in the 850 to 875 Fahrenheit range, is right at the nose of the temper and brittlement curve. And we got plenty of phosphorus there. So, you know, we're driving phosphorus to the grain boundaries doing that. Retempering at 1100 Fahrenheit, the bolts, I got 35 Rockwell C. They were within the spec range. They had a very high torque, 2,500 to 2,800 foot-pounds required to break them. And the fracture was ductile. One of my buddies at Bethlehem Steel and we took a bolt that had never been in service and we tempered it back. It was high hardness to begin with, but it wasn't it was never used. We tempered it back to 35 Rockwell C, and we made a fixture so that we could put this bolt and put the head on, or the nut on, and I got a 3-foot torque wrench and then a 3-foot extension to the torque wrench. And he and I are pulling on this while we're watching the torque meter. And of course, when it broke, we went flying across the room, but the fracture was totally ductile and no intergranular fracture or anything like that. So that's my conclusion on the analysis, and I think we're pretty close to on time. The failure analysis is really a fascinating field, and it requires you to have a full understanding of metallurgy. You got to understand process metallurgy. You got to understand design. You got to understand microstructure control, heat treatment, coatings, and you name it. And of course, service conditions and corrosion aspects and things like this. So you have to have a full knowledge of this range, because your failure study could involve any one of these aspects. And a lot of people, when they do a failure analysis, they just look at the first obvious thing that caused the failure and stop. Well, you know, if you correct that one big problem, that doesn't mean you won't have any more failures, because you could have other minor problems contributing to the failure as well. So you have to be thorough and really look at all the issues that are involved in any analysis. But, you know, metallography is a very important tool in failure analysis, Of course, mechanical engineers will do a failure analysis without ever looking at the microstructure. Just looking at applied stresses and things like that. And when they do any calculation for design, their first assumption is the metal is homogeneous and isotropic in properties. And no metal is homogeneous or isotropic. Perhaps a single crystal is, but we don't have single crystal structures out there. Certainly no bridge is made of single crystal steel. So, we have to take a total picture and understand all the potential sources for problems when we're doing our analysis. And then you get much better results. And you cannot be biased. A lot of court cases, the plaintiff who had the part that broke is going to hire a so-called expert, and they want that person's report to be kind of vague, and so they can sue as many people as possible, trying to get money from everybody. Yeah, I've seen this happen over and over, and there are several people that I've been against in court cases that lie under oath like crazy. And it's just unbelievable. I can't understand how any engineer can do that. But believe me, it happens. I often say that engineer is in the wrong field. He should become a politician. Right? They're used to lying.
Any questions from the audience? I think we had really very nice talks. We have seen the power of using metallographic tools metallographic techniques to understand, to design new coatings also, to protect our materials. And this can be extremely useful if you want to design a new material for a specific application. But at the same time, we have also understood that sometimes you have a failure, you need to understand what is the reason for that, to learn and improve your design, or understand if there is a mistake in production. So both aspects are extremely important, as George said. Arrigo Borin was discussing ceramic materials. He gave a very nice overview of classic and advanced ceramics. He also pointed out the differences between ceramic materials and metallic materials in mechanical features, also the thermomechanical properties. And we also understood in general that very often we have to understand, if I have to wrap up somehow the day, we have to understand and look at the problem from different perspectives, not only the mechanical perspective, but also the thermomechanical one. Sometimes also electric properties are important, and finally also corrosion. So environmental, chemical aspects have also to be taken into account. This, of course, complicates somehow the picture. We need to have somehow a multi-field perspective to our research, also to our design of new materials. And I think this is really challenging today. Still, there's still a possibility to improve and room for improvement of our design and so on and so forth. I don't know if there are questions. If not, please thank again all the speakers. It was a very, very nice morning.